Our next type of differential equation is Bernoulli's. Bernoulli's has this form: dy dx plus p of x times y equals q of x times y to the n. Now if you notice, it looks very similar to linear. The difference is this y to the n. And so what we're going to do is we're going to use this substitution, w equals y to the 1 minus n, and then it becomes Bernoulli, and then it becomes a linear, and so we can use our integrating factor, mu. So I've got two examples, and let's start with this one. Dy dx minus y equals e to the x times y squared. So if you notice, this is in the form I need it. So in this case, p of x is negative 1. So that's that p of x. The q of x is e to the x. And the n in this case is 2. So my substitution, w equals y to the 1 minus n. N is 2, so y to the negative 1. Now what I want to do is I want to substitute, get rid of the y's and only have w's, and it'll be linear in w, and I can use the integrating factor. So what this is 1 over y. So what I can do is I can make this 1 over w equals y. So therefore what I have is I have dy dx equals negative 1 over w squared dw dx. That's called the chain rule from Calculus 1. That's all I'm doing is the chain rule. So let's replace it. So this, using our substitution, so this would become negative 1 over w squared dw dx minus y, but y is 1 over w, equals e to the x, and this would be 1 over w squared. Now it doesn't look linear, but let's multiply everything by the coefficient of dw dx. The coefficient of dw dx, so let's multiply by negative w squared. Everything by negative w squared. So what do you get? You get dw dx. The minus makes this a plus. W equals minus e to the x. Now do not memorize the formula in the book. Just do this. And see, now I have it in the form of linear. So mu is e, the integral of 1 is x. So what do I get? I get total differential of w times e to the x minus e to the 2x, because it's e to the x times e to the x is e to the x plus x, and then dx. So what do I get? I get w e to the x equals minus, because I integrated both sides, so that'd be minus 1/2 e to the 2x plus c. So w is equal to, divide everything by e to the x. So I get w is equal to minus 1/2 e to the x plus c times e to the minus x. But what's w? W was 1 over y. Now, I can leave it like that. I can solve for y if you want to flip everything. But I mean, this is good enough as is. So this is my solution to this differential equation. Now let's take a look at this problem. Y to the 1/2 times dy dx plus y to the 3/2 equals 1 with an initial condition, y of 0 equals 4. Now if I look at this, this doesn't look like Bernoulli's. Not yet, but let's take this whole differential equation and let's multiply it by y to the negative 1/2. Or in other words, dividing by y to the 1/2. So what do I get? I get dy dx plus y equals y to the negative 1/2. Now, it's in the form of Bernoulli's. N in this case is negative 1/2. N is negative 1/2. So W equals y to the 1 minus a negative 1/2. So this would be y to the 3/2. So that's my W this time. It looks a little different, but that's what it turned out to be. So let's just go ahead and take the derivative. So dW dx equals, and I'll come down here, so that'd be 3/2 times y to the 1/2 times dy dx. Okay? So then dy dx equals, flip them, so this would be 2 over 3 times y to the 1/2 times dw dx. But the problem is, that's a y to the 1/2. I can't have y to the 1/2. So the question is, how do I get this in terms of w? Well, let's go right here. W equals y to the 3/2. W equals y to the 3/2. Let's take the cube root of both sides. So I get w to the 1/3 equals y to the 1/2. All I did was take the cube root of both sides. So now I can replace, and dy dx equals, well, y to the 1, so this would be 2 over 3, replace it, w to the 1/3 dw dx. So, coming back to our original differential equation, bring it down, replace, actually I'll go to this one, bring it down, because that one's easier than that. I still can do it there, but this one would be much easier. So I have 2 over 3 times w to the 1/3 plus y is again what? Well, I could solve for y right here. So square both sides. So I square both sides. So this would be w to the 2/3. I replace the y. This is 1 over y to the 1/2, so this would be 1 over w to the 1/3. So let's multiply everything, and I left out, of all things, I left out my w prime right here. Now, let's multiply everything by 3w to the 1/3 over 2. So, what do I get? Well, these guys cancel out, and I'm left with that w prime that I accidentally left out, dw dx, plus 3/2 w to the 1/3 times w to the 2/3 is w. The w to the 1/3 cancel out, so I get 3/2. Now look, and you see that I got it in the form of a linear equation. So mu in this case, e to the 3/2 x. Okay, so then what do I end up with? Total differential of w times the integrating factor e to the 3/2 x equals 3/2 times e to the 3/2 x dx. So I'm going to bring this over here. So integrate both sides. So this would be w times e to the 3/2 x equal to, so I got a 3/2, so I can just write this, that's nice, e to the 3/2 x plus c. So W equals 1 plus C times e to the minus 3/2 x. Okay, but what was W? Well, W going back here is y to the 3/2. So y to the 3/2 equals 1 plus c times e to the minus 3/2 x. But the one thing I haven't done yet is I have not taken care of my initial condition. Y of 0 equals 4. So let's plug that in. So y is 4, so that'd be 4 to the 3/2 equals 1 plus c times x is 0, e to the 0, so that's just 1. Well, the square root of 4 is 2, 2 cubed is 8. 8 minus 1 is 7, so 7 equals C. So, what do I have? Therefore, and I'll come right here and write my solution, y to the 3/2 equals 1 plus 7 times e to the minus 3/2 x. And again, I can leave it in that form. I could change it, simplify it if I wanted to. So again, Bernoulli's, it has to be in this form, dy dx plus p of x times y equals q of x times y to the n. Use this substitution. That makes it linear, and I use my integrating factor.